Hello, everyone. Thanks for this invitation and the opportunity. I am Vamsi Addanki from TU Berlin. I'm a third-year PhD student. Today, I will give you three perspectives on the performance of high-speed data center networks. I will not necessarily go into very technical details, but I will give you a high-level overview of our research, and hopefully towards the end of this presentation, I will be able to motivate you towards these problems. Just to be sure, is the audio and everything working well?
Yeah.
Cool. Let's proceed. To some of you who may not be familiar with data center networks in this context, this is how they look like. A large number of high-performance servers are interconnected together, and typically the entire network is operated and maintained by one or few entities. For instance, hypergiants such as Google, Microsoft, Amazon, they all have their own data centers to carry out their computation and storage needs. These networks can be represented in a slightly visually simpler manner. Most of today's data centers are flow-based topologies. We have the set of all servers that we would like to be interconnected. The servers are all arranged in racks. At the top of the rack, we have a switch that interconnects these servers, which we call intuitively as the top of the rack switches, or in short, we will hereafter call them TOR switches. All the TOR switches are then interconnected by a layer of spine switches. Sometimes we also refer to them as aggregation switches. And finally, the entire data center is connected. Every server can communicate with every other server. In this context, our goals are first high throughput. I will give a formal definition during this presentation, but intuitively it relates to the rate of transmission. We want to be able to transmit as fast as possible and be able to fully utilize the network capacity. Second, we want low latency, which is end-to-end in nature. Particularly, we are mainly concerned with flow completion times, which means the time it takes to complete a transmission. At the same time, we have an interesting catch here that we want the set of protocols running in the network to have very low buffer requirements. This special constraint is due to the hardware limitations in scaling up buffer sizes proportional to the capacity increases. These set of goals are especially challenging, first due to the nature of data center workloads. If we take a closer look at the distribution of the traffic flow sizes, interestingly, majority of the flows are short, whereas majority of the traffic volume comes from long flows. This puts a very tight tension between achieving high throughput simultaneously with low latency. At the same time, we see that the buffer sizes of data center switches are gradually decreasing over time. Here on the x-axis, we show a generation of data center switches arranged in chronological order from left to right, most recent being the right extreme. On the y-axis is the buffer available at each port per unit capacity. Clearly, we see that the buffer sizes are unable to scale up proportional to the capacity increases. So what could go wrong in such a network? Let's take a simple example. Say there is one flow shown in red here going from TOR1 to TOR2. Say there is another flow that joins in, transmitting from TOR-N to TOR2. Since both flows collide at the same destination, congestion develops at this point. As a result of congestion, first we face high latency, and in the worst case, innocent flows traversing the same path may experience very low throughput. Finally, due to the very nature of congestion, queuing builds up and buffer usage goes high, all three of which are against our initial goals. During this presentation, I will give you three perspectives with our goals in mind, which are high throughput, low latency, and low buffer requirements. First, at the server level, we will discuss congestion control at the transport layer. Second, at the top of the rack switch level, we will discuss buffer management and its potential in resolving congestion issues. Finally, at the network core, we will discuss on optimal topologies for our goals, specifically in the context of emerging technologies such as optical reconfigurable networks.
Could we ask questions?
Yeah.
So, in this case that you mentioned, I mean, there's communication between one server and another server. In data centers, I mean, you get the impression that flows, I mean, would be requests from external coming from the outside world to the servers, and not really between servers. Could you comment on the nature of the flows and why you take this assumption of
Yes, if we go back to the distribution of flow sizes, this is mainly, there are two types of traffic which we are mainly concerned about. One that is within the data center and the one that goes outside the data center. Most of the congestion problems are typically within the data center and typically at the very low end of the network core, which is at the top of the rack. Most of the time, there are high bandwidth links that go from the data center to outside world, and congestion is typically not a huge issue there. So we are, in this talk, we are mainly focused on intra data center traffic and how we manage that. And the traffic that emerges within the data center is mainly coming from exchanging information between the servers, or this traffic can also emerge from collaborative computations such as GPU computations and so on.
Just to complement what Vamsi said, basically there is this effect in cloud data center networks. There is a multiplicative effect because traffic comes from outside, but then this same request may be multiplied because you may spawn several instances, or you may basically multiply your traffic across different endpoints. So basically, a single outside request may correspond to hundreds of internal requests, and this is why the internal traffic may be amplified. It's called actually traffic amplification.
I just have a question also on my side to see how this can be implemented in real data centers. So you will have traffic, even if it is a small part of the global traffic, if you have more internal traffic than external traffic. How the external traffic, how is the internal traffic handled? I mean, maybe do you have, for example, a Tor which is connected to, instead to be connected to server, will be connected to blades that are connected to external links?
Yes, indeed. Here we are mainly looking only until the spine layer of the switches. Spine switches are then connected to so-called core switches or the border routers, which connects to the external world. Or this could even be connected to another data center somewhere located somewhere else. This is the traffic that goes out.
So the connection is made through the spine switches, not to the Tor switches.
No, yeah,
Okay,
exactly.
to my knowledge. Okay, thanks.
Yeah. So anything that goes out must go beyond the spine layer here.
Okay.
Shall we continue?
Yeah.
Okay, so moving on to the first perspective, which is the congestion control at the end host. Here, since it is at the end host level and at the transport layer, our visibility is pretty much restricted to a sender on one side, receiver on the other side, and possibly a bottleneck queue along the path. Within this context, today I will present you one of our recent work, PowerTCP, presented at NSDI 2022. So what is power and why do we actually call it PowerTCP? Let me give you a brief context of electrical systems first. This is a basic RC circuit. The potential difference across 2 points is what is called voltage. Current flows through the network, and power is typically the product of voltage and current. Similarly, we draw analogy to network systems in this work with sender, receiver, and a bottleneck queue along the path. In this context, we define voltage as the sum of bandwidth delay product and the queue length, which relates to the amount of data that is in transit across these 2 points. A current flows through the network as well, which relates to the total transmission rate. I will briefly introduce the notion of power during this presentation, so stay tuned for it. In a nutshell, PowerTCP is a power-based congestion control algorithm that can quickly react to congestion, but without losing throughput. It rapidly converges to equilibrium within just one round-trip time. It is fair and stable. And finally, it reaches our goals of achieving low latency and having high throughput. In this context, numerous algorithms were proposed in the past. We take a closer look at the fundamental rate control of each of these algorithms, and interestingly, we find that most of the existing line of congestion control works can be classified into 2 broad categories. We call voltage-based the class of algorithms that depend on a function of queue length, for instance, ECN, or round-trip time-based. The other category is the current-based, the class of algorithms that depend on a function of the total transmission rate, such as those that depend on gradients. To better visualize this classification, here we show on one dimension voltage-based class of congestion control algorithms that react to queue length, which is the absolute state of the bottleneck. On the other dimension, we have current-based algorithms that are reacting to variations in the network, which relates to the transient state of the network. Our key observation in this work is that existing approaches classified as voltage and current are fundamentally limited to a single dimension. We show this using a simple example. Let's consider a bottleneck queue which is growing in size. So now there are 10 packets, it's growing in size, 15, 20. And at this point, we have 25 packets. And consider that the queue is growing at a rate of 8 times the bandwidth. Similarly, consider another queue which has the exact same amount of queue length, but it is decreasing at a rate of at its maximum rate. The class of algorithms which we called voltage-based, those that are a function of queue length, cannot fundamentally distinguish between these 2 scenarios because the queue lengths are exactly the same, whereas one is growing in size, whereas the other is decreasing in size. Similarly, with another example where 2 queues differ in queue lengths, but they are both increasing at the same rate. In this case, the class of algorithms which we call current-based cannot fundamentally distinguish between these 2 scenarios because they only look at gradients, whereas the absolute value of the queue lengths differ. As a result, existing approaches are fundamentally limited to a single dimension, and they cannot distinguish between these 3 queues simultaneously in this example. Our analysis in this work and in summary shows that voltage-based class of algorithms can in principle achieve an equilibrium but they are very slow at reacting to congestion. Current-based, on the other hand, are indeed unstable. They do not have an equilibrium, but they do exhibit fast reaction to congestion. In a sense,
Please, could I ask a question? Could you explain why you have unstable for current-based? In a few words, why the?
Yeah. Let me try in the simplest way possible. So let's take this example. Okay. Current-based, by our definition, they are the ones that are depending on gradients, not the absolute value. So they stabilize when the gradient becomes 0, which means that they can stabilize at any particular Q length. So for instance, it could stabilize at, let's say in this case, 50 packets, or it could even stabilize at 25 packets. So by saying no equilibrium, it also means that it has infinite amount of equilibrium points. So it cannot really stabilize at a particular, it doesn't have a unique equilibrium. That's what we mean here.
Thank you.
Hope it's clear.
Yeah.
Yes, thanks.
Okay. So in a sense, the voltage-based class of algorithms offer us better in-flight control, whereas current-based algorithms offer us better reaction times. We ask ourselves whether we can systematically combine both voltage and current to offer the best out of the two worlds. As you may have guessed by now, power is still the product of voltage and current, but within the networking context here, voltage is the sum of Q bytes and the bandwidth delay product. Current is the total transmission rate. While this may sound crazy, why we simply multiply these two factors to create power, we emphasize this is not made up and it's indeed derived from the classical bottleneck link model. I will not go into further details for now during this presentation, but in the paper we show that the classical model throws out a very beautiful relation between the n-host congestion window on the left-hand side shown here and the product of voltage and current on the right-hand side. In a sense, the bandwidth window product relates to the product of voltage and current. I would encourage you to go into further details in the paper. In the interest of time, I skip it for now. In essence, power is a function of both Q length and the variation, basically both the absolute state and the variations in the network. This is a metric that can detect increased Q lengths. It can also detect sudden onset of congestion and the intensity. It can also detect rapid drop in Q lengths, thus avoiding throughput loss. Using this notion of power, we design a congestion control algorithm, which we call PowerTCP. At the core of PowerTCP is how we update the window sizes. The new window size is updated based on the old window size using multiplicative increase, multiplicative decrease, which is based on the notion of power with an additive increase, and the whole update is exponentially weighted moving averaged. All that differs compared to existing works is the multiplicative increase, multiplicative decrease that is now based on power, which brings us various interesting properties, such as maintaining high throughput, at the same time achieving low latency by catering towards both the absolute state as well as the variations in the network.
Can I ask a question?
Yeah.
So, I mean, power is associated with one queue, but on your way you have many queues, right? And many, I mean, you are having these layers of switches, right? And
Yes.
how can you extend this viewpoint compared to classical TCP
Yeah.
to a network? Since here I mean, it seems to be linked to one specific queue.
Exactly. It's linked to one specific queue. There is no way to combine congestion on multiple queues across multiple layers. But typically, most of the time in data centers, there is one queue along a path that experiences congestion. But in cases where we have a flow or a packet traversing multiple bottlenecks, we will consider the one that's most congested, because that's what we want to resolve first before acting on the smaller bottleneck. Does that answer your question?
Yes, and another related question. I mean, so in classical TCP, I mean, you have the feedback through the packet loss information. How do you inform the users of the power?
Yeah, this is actually coming up in the next slide.
Okay, sorry. Thank you.
Sure. So answering your question, the key enabler for how we measure power and how we inform the sender about the power calculations is in-band network telemetry. Let me show you by a simple example how this works. Our sender sends out a packet into the network. It now reaches the bottleneck switch. At this point, the recent advancements in the switches being programmable and more recent advanced hardwares allow switches to append certain telemetry or metadata into the packet, which is then transmitted to the receiver. The receiver can echo back the same metadata into the acknowledgement. And finally, the metadata that was inserted by the switch reaches the initial sender. With this information, we are now able to calculate power and take a more informed decision over how to react to congestion. I will briefly present some of our evaluations on PowerTCP first. All the evaluations are based on NS3 simulations. So we first evaluate PowerTCP in an incast scenario. By incast, we mean that multiple flows collide at a common bottleneck at the same time. Here, at time 0, 10 flows hit the same destination. On the x-axis is time, and on the y-axis, shown in blue, is throughput on the left, and on the right is queue length, shown in red. The reason we are concerned more about queue length here is that it directly relates to latency. So lower queue lengths are good in terms of latency. As we see, PowerTCP is able to quickly react to congestion and rapidly resolves it without losing throughput. In comparison, here, Timely is a congestion control algorithm along similar ideas, which was indeed used by Google data centers until a few years ago. It not only loses throughput, but is also unable to resolve congestion as quickly as PowerTCP. HPCC here is another congestion control algorithm which was developed by Alibaba. It also exhibits both loss in throughput and increased latency compared to PowerTCP. In terms of stability and fairness, our evaluations show that PowerTCP remains both stable and fair across multiple flows. This is an experiment where there is a single flow at the beginning, and more flows join as time passes by, and finally each flow leaves the system. Our interest here is whether the control law converges to a phase state and remains stable as new flows join and leave. As we see, comparatively, PowerTCP remains much more stable and fair relative to the counterparts. As we discussed earlier, our goal is also to reduce latency in terms of the completion times, which is the time it takes to complete transmissions. In this evaluation, we see that PowerTCP significantly outperforms the state-of-the-art, even as the load increases in the network. In summary, what we've seen so far is that existing congestion control algorithms are limited to a single dimension. Power is an interesting and probably good metric for congestion control. And finally, it reaches our goals on throughput, latency, as well as having low buffer requirements. You can check out more updates in future on this website. We could take 1 minute of questions at this point before moving to the next part.
I have a question on my side. In the last line, you said I did both things for short flows and long flows. But is there any discrimination between them, or are there some flows that are better served by PowerTCP than other ones because of their size?
Ideally, we would want to have flow completion times as low as possible, as close to ideal as possible for all the flows. But why we explicitly write for both short and long flows in this slide is that typically, if we do not serve long flows at all, we are basically underperforming or rejecting most of the traffic volume. If we go back to the distribution of flow sizes, let's see here. Yeah, so by underperforming or serving less of the majority traffic volume, which is coming from long flows, we have very minimal congestion remaining in the, there could be cases that there's no congestion at all by simply rejecting all this traffic, and short flows are mostly getting their ideal completion times, which is not really good in the sense that we are not performing well in terms of throughput in this case by rejecting the majority of traffic. So ultimately what we want is to serve both these two types in terms of their completion, which ultimately results in throughput and latency dimensions together. Hope it's clear.
Yeah.
Perhaps another question. So, I mean, if I get it, if I remember well, you have a multiplicative decrease and additive increase, right? Is it right?
It's multiplicative increase and multiplicative decrease.
Okay. So could you come back to the equation?
Yeah.
Okay.
There is an additive factor here, which is separate to the multiplicative increase and multiplicative decrease.
But what is beta here then?
This is an additive increase, but this is a constant additive increase.
Okay, so it's why I thought it was additive. But why do you call it multiplicative decrease since there is beta? Because of this, I think.
The multiplicative increase and multiplicative decrease is because of this particular factor, which can either increase or decrease multiplicatively. The additive increase is just a constant here, whereas this particular factor depends on the power that we measure.
I see. And then how do you tune E and beta?
So beta relates to the equilibrium point that we ultimately reach. This is a tiny detail that we explore more in detail in the paper, but To put it in a simpler way, beta is necessary for maintaining fairness, and it also relates to the equilibrium point that we reach. Whereas multiplicative increase and multiplicative decrease, this is essential for faster reactions, and it is, I think it's clear so far.
Okay, thank you. So actually, there is a mix of multiplicative increase and additive increase. It depends on how E and F behave, but there is also an additive increase. Okay, thank you. Thank you.
Yeah. So the whole control law is a mix of multiplicative increase, multiplicative decrease with an additive increase. But the place where we use power, this is purely multiplicative increase and multiplicative decrease. Power does not factor into the additive increase. This is just a constant here.
Does one know the equilibrium? I mean, if you get fluctuations, I mean, does one knows for TCP, Reno, or others, I mean, classical things. Does one know the equilibrium points or the of this type of dynamics?
Could you repeat? I fully did not follow.
Well, did you study the equilibria for this type of dynamics?
Yeah, exactly. We do have few more theoretical results in the paper on equilibrium and exactly what equilibrium point it reaches. Indeed, we show some results on stability as well. We show that the control law reaches Lyapunov stable criteria. And if I'm not wrong, we should also have some results on convergence and the convergence time also.
Thank you.
So moving on, so far we've seen how accurate congestion control can alleviate some of the problems of congestion and achieve high throughput, low latency with low buffer requirements. However, multiple bottlenecks and congestion events could occur simultaneously within the same switch. This is particularly concerning since all the queues in a switch share a common buffer space. Typical data center switches are equipped with a memory management unit, which provides a shared memory region. This buffer space is shared across all the queues in the device. As a result, congestion on one queue could potentially interfere in an unpredictable manner with other queues in the device. In this context, I will now present ABM, Active Buffer Management in Data Centers, which is a recent work which appeared in SIGCOMM last year. I hope some of you in the audience are familiar with these two famous keywords in networking, active queue management and buffer management. Indeed, the answer to what is ABM lies within this slide. Let me put it into perspective. On one hand, we have active queue management that aims to control queuing delays. For instance, ECN-based approaches like RED, some approaches such as trimming-based and delay-based, classical examples like CODEL. Overall, AQM class of algorithms aim at providing stable queuing delays. On the other hand, we have buffer management schemes that are acting over the entire device-wide queues, and they aim at controlling the total shared buffer occupancy. A classic example here is the dynamic thresholds algorithm. Buffer management schemes offer better isolation across traffic priorities. Our key observation in this particular work is that burst absorption requires both isolation as well as stable queuing delays in the steady state. We are concerned about burst absorption specifically in this case because absorbing transient bursts is of utmost importance to avoid transient packet drops, which leads to latency blowup. Within the space, we propose ABM in this work. In summary, ABM is a buffer sharing scheme for data center switches. It is not an independent combination of AQM and buffer management, but intuitively it can be visualized as AQM that depends on buffer management. We hence call it active buffer management. It provides isolation across traffic priorities. It provides bounded queue drain time, or in other words, queuing delays. And finally, provides better burst absorption. Before going into further details, let me give you a brief background on buffer sharing. Both buffer management and queue management calculate drop thresholds within a switch device. First, buffer management calculates a threshold for every queue in the device. And this typically depends on a function of the shared buffer space, which is the aggregate shared memory region available to all the queues. AQM, on the other hand, is local to a single queue. It calculates thresholds which are a function of the local queue statistics. Importantly, both buffer management and AQM, they act independently. This results in a hierarchical admission control scheme where upon a packet arrival, first buffer management takes a buffering decision and passes it on to the active queue management module. And finally, a packet is either dropped or put in the buffer. Concretely, first, buffer management calculates a threshold. This threshold is compared against the corresponding queue length, and if the threshold exceeds the queue length, the packet is enqueued. Similarly, AQM does the same job by calculating a threshold, but the only difference is that the now threshold is depending only on the local queue statistics. Finally, the packet is either enqueued or dropped. Here, it's interesting to observe that this hierarchical scheme results in a joint threshold, which can be expressed as minimum over the thresholds calculated by buffer management and queue management. By the very nature of the function minimum here, either buffer management or queue management threshold is active at the same time instance, but not both or any function of both. So suppose we have very large buffers in the network. Buffer management simply buffers every packet since there is enough remaining buffer always. In this case, AQM becomes more important. In contrast, if we have shallow buffers, which is the case in the data centers, then there is so little buffer that AQM is not triggered in the average case, and buffer management becomes more important in this case.
I just have a question on this, just to try to understand what are the things that inside this management. Can you reverse the order? Is there a change if you reverse the order? Because the formula you give seems to be symmetrical, but I think the order should be important. Can you have AQM before BM?
AQM before BM. I'm not sure if the hardware today is flexible enough to do that, because it's mostly relating to hardware and how it works, because once a packet enters a switch, it has to be put in some buffer space. And in order to do that, first the memory management unit comes into action, which is taken care of by buffer management. Later on, AQM is more relating to how to maintain a single queue. So AQM takes a second or a special decision later, but whether to put this packet in the buffer for further processing or not is first taken care of by buffer management.
Okay. Okay, thanks.
So what distinguishes between these two types is buffer management acts device-wide across all the queues, and AQM is local to a queue. So given that in shallow buffers, buffer management becomes more important, we hereafter focus mainly on the drawbacks of the state-of-the-art dynamic thresholds algorithm. Simply put, it calculates a threshold for each queue across the entire device as a product of alpha parameter that can be configured for each priority, and which is then multiplied with the total remaining shared buffer region. This allocation scheme results in the overall occupancy for each priority as a function of the number of queues of priority P using the buffer. What's interesting here is how the allocation depends on the number of queues of priority P as they increase. So our analytical models show that dynamic thresholds and this particular allocation scheme results in two main drawbacks, which is priority inversion and that the allocation is oblivious to buffer drain time. I skipped the analytical details in the interest of time, but in this plot, we see more graphically how the allocation results in priority inversions. We consider two priorities, one shown in black, which we will consider as low priority, and priority 2 shown in red, which we will consider as high priority. On the x-axis, we will increase the number of low priority queues using the buffer, and on the y-axis, we will see how much buffer is allocated to each priority. As we see, as the number of queues of low priority increase, the allocation scheme allocates more and more buffer to the lowest priority, leaving very little buffer available for the highest priority. At some point, this results in priority inversions. Second, the allocation scheme is oblivious to buffer drain time. That is, it allocates buffer irrespective of what the queue drain rate is. For instance, consider this example where two queues have the same queue lengths across two different ports, I1 and I2. Although these two queues have the same queue lengths, they differ significantly in terms of queuing delays because the first queue shares its bandwidth with two other queues, whereas the second queue has the entire bandwidth of the port available for itself. In summary, our analysis shows that buffer management schemes can, in principle, offer isolation across queues, but they are oblivious to buffer drain time. AQM schemes can, in principle, offer bounded queue drain time, but they cannot fundamentally satisfy isolation properties. In this work, we aim at three main goals. First, isolation. Second, bounded drain times. And third, burst absorption. Interestingly, burst absorption relates to the previous two goals. So what we are looking for is not just a hierarchical scheme, but with buffer management and AQM as a function of both. Within this space, we propose ABM in this work. Our main building block is the classic dynamic thresholds algorithm. However, as we saw, this has two main drawbacks. We first introduce a new factor to resolve priority inversion. This factor is the inverse of the number of congested queues that helps us to resolve priority inversion. In other words, we now take care that the allocation doesn't grow unboundedly as the number of queues of a certain priority grow. Second, a very simple AQM based on delay could easily resolve our second problem of oblivious to queue drain time. But we still do not want a hierarchical scheme with buffer management and AQM side by side. We propose a new buffer allocation scheme, which combines the ideas of both into a single allocation scheme, finally resolving both the key drawbacks that we discussed before. The threshold calculated by active buffer management is based on a configurable parameter alpha multiplied with the inverse of the number of congested queues, which takes care of the priority inversion problems, multiplied with remaining shared buffer space, which introduces a certain dynamicity in the threshold calculations, meaning that it's adaptable to the load changes, which is then multiplied with normalized DQ rate, which takes care of the drain time problems. Overall, this allocation scheme can be visualized as an AQM that depends on buffer management. ABM has some interesting properties. First, it upper bounds the buffer allocated to a certain priority, which is essential to prevent monopoly. It also lower bounds the buffer allocated to each priority, which is essential to provide certain amount of minimum buffer that is available to every priority at all times. Finally, ABM also upper bounds the queue drain time to provide bounded queuing delays. Maybe let's take one question here. I will skip to the next part from here.
Also, I have one question. So this adaptive thing, I mean, could it be replaced like a static network calculus type scheme where you would also bound with priorities, buffer size and delay? Is it possible to obtain, I mean, not equivalent, but similar type of results with just, I don't know, regulating the input flows? Using network calculus ideas?
Sounds interesting. Definitely could be worth a try. But one key aspect to keep in mind here in this formulation is that different queues use the same buffer region. So if one queue grows in size, the buffer available for the other queue gets affected. So that's the only catch here. Definitely, classic ideas could definitely be used here.
Thank you.
Since we are going a little bit over time, I will skip the evaluation for this part and go to the more interesting last part. Finally, while we are able to optimize the performance using congestion control and buffer management techniques, the topology itself imposes certain limitations in terms of scalability. Recent studies show that as the data center network demand increases over time, the switch capacities are unable to scale up proportionally. And this is mainly due to the CMOS semiconductor scaling limitations. This poses a fundamental question whether the current topologies based on electrical packet switches are ready for the explosive growth in data center traffic volume. Thankfully, new technologies are emerging and the networks are now based on pure optics, which are on the rise. This is just one example of many technologies that emerged during the recent years. The transmission of data from the endpoint is through a tunable laser that emits light. A simple piece of glass called arrayed wavelength gateway gratings act as switches. Based on the color emitted by the tunable laser, the grating can now switch across multiple ports. Recent advancements are exciting in terms of the latency to reconfigure. These tunable lasers are now capable of tuning the color of wavelength of the emitted light at nanosecond timescales. Further, since the switch is just a piece of glass without much electrical power needed, they are future-proof in terms of bandwidth scaling. But there is still a catch here. Switches are now bufferless and circuit switched. In this context, I will give a short overview of our most recent work, which is Mars, where we study the fundamental trade-offs that arise in such networks and propose a near-optimal throughput topology within this design space. We will first convert this representation of data center topology to a slightly more simpler manner. First, for simplicity, we show the network at the top of the rack layer. We remove the servers from this representation and consider that the top of the racks are now generating traffic into the network. We also split input and output in this representation. What is interesting and what changes from static electrical networks we saw before is the spine layer, where switches are now circuit switched and they can change over time. The configuration changes over time. At each time instance, the circuit switch connects each input port to an output port using a matching. We are allowed to configure as many matchings as we want, which will be executed sequentially, but they repeat periodically. Each matching stays for a duration of delta, which we call time slot, and it takes a certain amount of time to reconfigure and change to the next matching. The entire sequence of matching that we configure takes gamma amount of time slots, which we call as period. As a result, this representation of our topology is effectively a periodic graph, which changes over time, and the sequence repeats periodically. It is interesting to see that this periodic graph essentially emulates, in a certain way, a static graph over time. But before going into further details, let me first define what we mean by throughput here. We have a demand matrix, which specifies the demand between every Tor pair in the network in terms of bits per second. Throughput is the highest scaling factor such that the scale demand is feasible in the network. What we mean by feasible in the network is that there exists a feasible flow that satisfies the scale demand, which is subject to flow conservation and capacity constraints. A very quick overview of our results here are that the first important result here is that the throughput of a periodic evolving graph is equivalent to that of an emulated graph that it emulates over time. This indeed enables us now to study the throughput of this graph that changes over time by simply looking at its corresponding static graph, where we have a lot of tools, a lot of techniques in the literature to play with. Given that now we are able to study periodic graphs using an equivalent static graph, we also give the throughput upper bound for static graphs, which can now be traced back to what is the throughput of the periodic evolving graph initially that we were looking at. We then also study delay and buffer constraints within the same network, but let me show you in a more graphical manner what we achieve here. So the big question here we study in this work is, given a periodic graph, it emulates a certain emulated graph, and what emulated graph achieves the highest throughput, lowest latency within the buffer constraints that we have. So we are mainly concerned about the degree that we emulate over time. What we observe is that as the degree increases, going from simply remaining static to changing over time and increasing our graph node degree, we can indeed increase our throughput, but at the cost of increased delay. Suppose we restrict our buffer availability, we have an interesting pattern here that now, compared to a static graph, we have much worse throughput by changing over time and having a higher degree. This leaves us with an infeasible region for the design space and a very small feasible region for the design space under restricted buffer constraints. At this sweet spot where we maximize throughput, minimize delay within the available buffer is our work Mars. And I invite you to have a look at our paper. Thank you, and you can take some questions now.
Thank you. I have a question on the last part of your presentation. So at the beginning, you were talking about changing periodically the cross-connect arrangement in optics in order to get some graphs that change with time, but in a fixed manner, in a not tunable manner. And then at the end, it was not really clear for me. You talked about the possibility to adapt. Maybe if I well understood, there is a possibility to adapt the graphs that you repeat in time according to the traffic demand. Is it right?
Yeah.
Do you have a schedule to do that?
This is actually going to be our future work now, as is ongoing. So far, in this particular work, we only look at demand oblivious. We fix it once and it repeats over time periodically using the same set of matching. So everything is predefined, but we always have the possibility to look at the demand, maybe adapt to the demand and try to optimize there. This, interestingly, this comes at the cost of some latency, which is more systems oriented problem. That is, if we were to look at demand and do some optimization, this has certain latency and our reconfiguration time typically increases, maybe not at nanoscale, but we could probably go at millisecond scale. That's a trade-off there.
Okay. Question in the room? François?
Perhaps on the first part on this extensions of TCP, I mean, is there a hope to extend some of these ideas to networks where there are several congestion spots, not just a single bottleneck? I mean, could you extend this TCP, this variants of TCP to more general structures without? Because you said that you had physically that only there was one bottleneck on each path, right? But assume it would not be the case. I mean, is there a way to extend this notion?
Yeah, actually, most of our modeling is on a single bottleneck link, but in practice, how we use it in simulations and in the evaluations is once a packet traverses multiple bottlenecks along the path, it carries the metadata or the power values from every hop along the path, and the sender is looking mostly at the highest congested link. In this way, we can extend it directly to more general networks, not just a single bottleneck. So essentially, instead of saying single bottleneck, it would be the most congested bottleneck. Okay. And the decision or the criteria for most bottleneck would be by looking at all the metadata from every hop and then deciding which one is most congested.
But under this scheme where you do that, I mean, can you prove properties of the network in terms of stabilization for general topologies? I mean, this worst case.
This would be a little bit technical challenge from analysis point of view.
Okay.
Yeah.
Thank you.
I have another question on my side. So that will mix the three parts of your presentation. One may envisage to mix the three solutions together. So you will have end-to-end traffic control, buffer management within the switch, and the topology optimization in the interconnection between the different switches through optics. Do you plan to have some in the future work to have some studies in terms of the interaction between the three parts? Maybe the time scale are different, so it maybe can be done for some on some aspects. I don't know. So
yeah. This is the hope. I will have to wait and see how it works out.
Okay.
And in the larger picture, definitely yes.
So, okay. Other question in the room? On the bridge? So thanks again.
Thank you.